In this experiment, we will be synthesizing a metal oxalate compound and then characterizing it using a redox titration to determine the mole ratio of oxalate to compound, and that will allow us to actually determine a at least good guess on what the chemical formula for the compound must be. And so in this experiment, there are 3 different metals that are possible to work with, and you could choose from iron, copper, or cobalt. But the goals of the overall experiment would be that you can first synthesize your metal oxalate with your desired metal as a group, and then you can use the redox titration in combination with some calculations you've done on the possible compositions to determine a possible theoretical mass of oxalate compared to the rest of the compound mass. And you can take that information to determine what the chemical formula of your compound probably would be. And the last goal is that once you know your formula, you can take the mass of product that you weighed after synthesizing and determine a % yield based on the stoichiometry of the reaction. And so first, let's go into a little bit of background on coordination chemistry, just in case your class has not quite caught up to where we are in this experiment. A coordination compound is made up of a transition metal atom bonded to a certain number of ligands, and this N is here to represent however many moles of ligand are present. L is just some generic ligand. The combination of that metal and ligand, though, forms a coordination complex. And coordination complexes are typically charged species as a part of an overall compound. So in order to make it into a compound that you can actually precipitate as a solid, usually you have to have a counter ion present to make it a neutral and therefore potentially solid crystallizable compound. It could be that your ligand complex is a positive charge, therefore your counter ion would be a negative charge, such as a halide. But you could also have where your complex has a negative charge and your counter ion has to have a positive charge to balance that out, such as one of our alkali metals. And so the general formation of these complexes involves the electrons from a ligand being donated to a positive metal ion. And so this metal ion is deficient in electrons. The ligand has excess electrons that can be shared, and that leads to this type of bond, which is called a coordinate covalent bond, also known as a dative bond. It is a little different from how we would think of a typical covalent bond, where you have 2 nonmetals interacting and doing a bit more sharing of the electrons. In this case, we can think of it more as a donation, but a donation that keeps the 2 parts together. So it's a bit more polarized in that sense. So the metal then would be considered a Lewis acid because it is accepting electrons, and the ligand would be considered a Lewis base. And so it's really a coordination chemistry that makes the definition of Lewis acids and bases come to life for us. So you could have it as a neutral ligand donating a lone pair, but oftentimes you'll also see ligands that have a negative charge and still have some lone pair that can be donated. It's pretty much always going to be a lone pair that is involved in this kind of dative bonding. All right, so now that we've talked about the actual types of bonding going on, metal centers can form complexes with bonds. In a typical structure you might see is 4 bonds to ligands or 6 bonds to ligands. These are the most common. So we're going to look at some examples with 4 bonds to ligands, but it may not be that all four bonds are to separate ligand molecules, you might have a ligand molecule that can bind from two separate spots on the molecule. So this is just a generic way we could write a bidentate ligand with nitrogen atoms that donate their lone pairs. So let's imagine that these two nitrogens are connected by some carbon structure. They each had a lone pair that they're able to donate to that metal center. And we have another one on the other side. So we're forming a coordination complex with a coordination number of 4, and we count that based on the number of bonds to the center. But because each ligand is donating twice, we call it bidentate, so it only has 2 ligands with a coordination number of 4. The analogous ligands that are monodentate are these ammonia ligands, and each one is separate from each other, and there was a lone pair on the nitrogen that is being donated to the metal, and so we have 4 separate nitrogen atoms on 4 separate ligand molecules. Now, this again has a coordination number of 4, but it's also 4 ligands because they're each monodentate. The shape of each of these molecules would likely be very similar. They would likely either be tetrahedral or square planar, and we would have to know some more about how these ligands operate to be able to determine that. But one important key difference between mono and bidentate and tridentate, you could have ligands that bind more than 2 times depending on the structure, is that as your denticity increases, so the number of times it binds to the center atom, you get a stronger binding of that ligand. And it kind of makes sense because each of these molecules is only holding on with 1 lone pair. But when you get up to a bidentate ligand, you have the molecule with 2 separate lone pairs holding on to that metal center. So it makes sense that it would be a stronger binding overall. And that's actually going to be the driving force for the reaction that we are going to do in our synthesis for this lab. We're going from monodentate ligands to bidentate ligands, and that is a stronger bond in the final structure. And so the possible metals already mentioned are iron, copper, and cobalt, and these are their oxidation states that will be present in the compounds we're synthesizing in this lab. But they're going to represent our metal center, and we will have in each chemical formula 1 atom of the metal. We will have some unknown number of oxalate ligands attached to that metal, and it could be somewhere between 1 to 3. So you will have to determine that ratio. Is it a 1-to-1 ratio of metal to oxalate, a 1-to-2, or a 1-to-3? And so you'll get your complex, and in order to actually precipitate it, it will need to be forming a counterion, or forming a compound with a counterion in most cases. The counterion being used will be potassium, and you could have anywhere from 0 to 3 potassium atoms. But in some cases, you will also have water present in all 3 structures. You will also have water present either as a ligand or as what's known as a hydrate. And that's hydrates are kind of common with metal compounds. That's just part of the solid because they like to absorb moisture from the solution they're in when they form the compound, or from the air around them. And so every formula is going to have either 2 or 3 waters in it as well. But based on these provided values, which are also provided in the table in the protocol, you can come up with what the possible chemical formulas would be based on these numbers and calculate theoretical mass percent of oxalate in each of those complexes. So if there were, for example, 2 oxalates, 1 metal, 1 potassium, and 2 waters, you would add together those masses and also take the mass of just oxalate times 2, because there were 2 of them in that formula, and divide the mass of oxalate by the overall mass of the chemical formula. And that would give you your theoretical mass percent of oxalate from that possible iteration of the chemical formula. If you were really thinking about this before you go through and just calculate every possible combination, you could think about, well, what would the charge of this complex be then, and how many counterions would be necessary, and that'll give you a little bit more ability to narrow down your options, which I recommend. Makes the calculations a little simpler, but again, if you don't want to think that hard about it, you can split up these calculations amongst the team, and it shouldn't take too long with the limited number of options. So essentially, the overall formula is going to look something like this. You can figure out the values of x, y, and z when you actually know the relationship between the number of oxalate ligands compared to your one metal atom. You will have already calculated the theoretical mass percent, and so that will allow you to fill in the other values based on how you had calculated that theoretical value in the first place. So to do this, we're going to take a known mass of our complex that we don't know its formula. We're going to titrate that known mass, and we're going to get what the actual mass percent is. And we can calculate that, calculate the actual mass percent, compare it to our theoretical mass percents, and that should give us a pretty good guess as to which formula is accurate. You can also calculate percent error there to show how far off your value is compared to what you would expect if you did a perfect titration. All right. So the idea is that the type of titration we're doing is not like the typical acid-base titrations we've seen in the past. Instead, we're doing a redox titration. And titration really works with any kind of chemistry that gives you only really a forward reaction. And so to do this, we're taking a strong oxidant, the permanganate ion. This permanganate ion is manganese in its 7+ state. It really would like some electrons, so it's a pretty strong oxidant, and that leads to a mostly forward reaction. We will react solutions of permanganate, which is a dark purple color, with our oxalate solutions until we get the solution to turn light pink and it doesn't change anymore. Now, we'll be carrying out this reaction with our prepared compound because it has oxalate ions in it, but we will first need to take that permanganate solution and precisely measure its concentration, which is known as standardizing titration. And so that's the first part of the titration process, is to take permanganate, react it with a known mass of sodium oxalate. So the sodium oxalate, we know its formula, we know the relationship between mass and moles for it. When we do the titration, that will give us a known volume of permanganate. And so if we know the mass of the sodium oxalate in solution, we know how many moles there were. If we know the overall balanced redox reaction between oxalate and permanganate, which you will have to figure out as part of your pre-lab, we know what the stoichiometric ratio is, so we can convert moles of oxalate into moles of permanganate. And combining the moles of permanganate with the volume of permanganate measured, we get the concentrations. That's the overall process for the standardization. Once we get to the titration of our complex, we will have a known mass of our compound, and we will have a known concentration of our titrant because we just standardized it. So therefore, we can use the burette to measure out specific volume. The volume of the concentration will tell us how many moles of permanganate were required to completely react with the moles of oxalate present. And we'll again use that same stoichiometric ratio to work our way back to how many moles of oxalate must have been present. If we know how many moles of oxalate were present, we know the mass of oxalate present, and we can get a mass percent of oxalate out of our measured mass of our compound. That is the basic theory behind this experiment, but hopefully you can get small enough error that you can make a reasonable guess on your chemical formula, as well as get a reasonable value for your percent yield.